So, good evening, sir. My name is Prakhar Patwardhan, and I'm here to present my topic title. The topic title is Swan Optimization in Gear Design. So, the course is a process design, and the course for this 2078. So, the content of the PPT that I've made are introduction, importance of Swan Optimization, type of Swan Optimization algorithms, Swan Optimization in Gear Design, factors affecting gear design, pathing code, output, and reference. So basically, the first topic is introduction. So Swan optimization algorithms stimulate self-organized behaviors found in nature to search for optimal solutions efficiently. Each algorithm involves multiple agents that work collaboratively to explore and exploit the solution space. So key characteristics are decentralized control. So no single entity governs the process. Self-organization, the system adapts dynamically. The third one is collaboration and communication. So the agents share information to improve solution. The fourth one is simple rules and complex behavior. Each agent follows basic rules, but the collective achieves an optimal result. So second point is importance of swarm optimization. So the first one is efficient problem solving. So finds near optimal solution for complex, non-linear, and high-dimensional problems suitable for problems where traditional mathematical model fails. Second one is adaptability and robustness. So works well in dynamic and uncertain environments. Self-organizing nature makes it robust to change in the problem space. The third one is no need for gradient information. So unlike traditional optimization methods, one optimization does not require derivative information, making it useful for non-continuous or non-differentiable problems. The fourth point is scalability and parallelism. So it can handle large data sets and multi-dimensional problems efficiently. Works well with distributed computing and parallel processing. So another section in my PPT is of types of swan optimization algorithms. So the first one is particle swan optimization (PSO), so which is inspired by bird flocking. The second one is ant colony optimization (ACO), so modeled after ants finding food. The third one is artificial bee colony (ABC), so which mimics bee foraging behavior. Fourth one is firefly algorithm, inspired by firefly attraction mechanism. Fifth one is BAT algorithm, based on BAT's equation for navigation. So the first topic that I will tell from the types of phone optimization, ant colony optimization. So in ant colony optimization, it is the nature-inspired optimization algorithm developed by Marco Dorigo in the early 1990s. It is based on the foraging behavior of ants, particularly how they find the shortest path between their nest and food source. Ants communicate using pheromones, leaving chemical trails, and that helps other ants follow optimal routes. Over time, stronger pheromone trails reinforce better paths, leading to convergence towards the best solution. In ACO, a group of artificial ants explores a problem space where each ant constructs a solution by moving through possible choices. The probability of selecting a path depends on the amount of pheromone deposited and a heuristic value, such as distance in routing problem. So the applications of ACU are network routing. So it optimizes data transmission paths, logistic and supply chain, finds the most efficient delivery routes, urban vehicle routing. So it helps in planning optimal travel paths. Fourth is scheduling problems, using job shop scheduling and resource allocation. The fifth last one is bioinformatics. So it is applied in DNA sequencing and protein structure prediction. So in ant colony, basically ant we have seen in real world situation where ant takes a shorter path to go to its desired location. So ant colony optimization is based on such practical real life application. Second is particle swarm optimization. Particle swarm optimization is a nature-inspired optimization algorithm developed by Canadian Behart in 1995. It is based on the collective behavior of social creatures such as bird flocks and fish schools. To find optimal solutions in multi-dimensional search space, PSO consists of a swarm of particles, each representing a potential solution. These particles move through the search space and adjust their position based on their best known position and the global best position of the entire swarm. The moment of particles is influenced by their velocity, which is updated at each iteration using a mathematical formula that balances exploration and exploitation. So applications of PSO are engineering optimization. So first is structural design, circuit optimization. Second is machine learning, neural networks, training and feature selection. Robotics, path planning and so on, robotics. Finance, portfolio optimization, stock market prediction. Healthcare and bioinformatics, disease diagnosis, medical image processing. So in swan optimization, about coming to the application part, we have seen that in machine learning we are using neural network is a major what we call it's a major branch of machine learning. So swan optimization and gear design, which I have done. So swan optimization techniques such as particle swan optimization and ant colony optimization have been increasingly used in gear design and optimization to enhance performance, efficiency, and durability. These algorithms mimic the behavior of natural swans to find the best design parameters, reducing weight, improving strength, and minimizing gear failures. Key objectives of gear optimization are minimizing weight, reducing the material usage while maintaining strength, maximizing strength, enhancing gear durability and load bearing capacity. Third one is reducing friction wear and optimizing tool profile to improve efficiency. Improving efficiency, minimizing energy loss due to transmission error, loss in noise and vibration reduction. So optimizing gear tooth modification to lower operational noise. So factors affecting gear design are the first is design parameters. So the module. So basically the module determines the size of the gear teeth. It affects load distribution and strength. The number of teeth influence gear ratio, smoothness of operation and wear resistance. Pressure angle typically 20 degree to 25 degree affects contact force and efficiency. Helix angle to impact noises, smoothness and load distribution. Face width, wider face increases strength but may lead to misalignment issues. Define speed reduction or amplification in the system. Second is material properties. So hardness and strength determines resistance to wear and fatigue. Steel versus plastic gears. Toughness is ability to withstand impact loads. Third one is surface treatment, case hardening, nitriding or carbonizing improves wear resistance. Uh, Fourth one is self-lubricating materials used in polymer gears for reduce friction and maintenance. And the third point is manufacturing and tolerance factor. So in gear tooth accuracy, poor manufacturing can lead to noise, backlash, and reduced efficiency. Surface finish, smoother surface, reduce friction and improve efficiency. The third one, profile modification. It prevents edge contact and reduces stress concentration. Fourth one is operating conditions. The load conditions, excessive load can cause tooth bending, pitting, and fatigue failure. Second is lubrication, so it reduces friction wear and heat generation. Incorrect lubrication leads to premature failure. Third one is temperature variation. The thermal expansion affects gear meshing and alignment. Fourth is contamination and debris. So foreign particles can accelerate wear and cause damage. The fifth one is dynamic factors. So vibration and noise. So misalignment, backlash, and improper mounting led to excessive vibration. The shock loads. So sudden load can change and can cause tooth breakage. Misalignment is incorrect installation, affect contact pattern and increases stress. So for my presentation, I have written one Python code. So before coming to Python code and how I've linked that Python code with robust design and Taguchi's method. So first I will brief you with this. So basically to incorporate Taguchi robust design method into Swan optimization for gear design, I have done so basically use Taguchi's orthogonal array to reduce the number of experiments while covering a wide range of parameters combination. Second is calculate signal to noise F by N ratio where Larger the better for strength stress ratio, smaller the better and for volume and weight. So I use particularly Swan optimization to find greatest gear parameters while ensuring robustness. So what's new? So in Taguchi's orthogonal array, it stimulates 9 test cases per parameter set to measure robustness. Signal to noise ratio, F by N ratio, so it minimizes the sensitivity to manufacturing variation. PSO optimization finds the best gear parameters using robust performance matrices. Confusion matrix simulates a classification problem for robustness validation. So why we are using this? So to ensure stability. Taguchi's method reduces sensitivity to parameter changes, more efficient optimization. So it uses only 9 experiments instead of exhaustive testing. Practical for real world for manufacturing reduces real failure rates and improves reliability. So simple explanation of the project I've done that we are designing a gear that works well if even if manufacturing or material properties vary. So how I've incorporated Taguchi in this. So instead of testing various possible designs, we test only a few smartly chosen cases. It helps find a robust design that performs well in all conditions. Particle swarm optimization (PSO). So works like bird searching for food. Each bird gear design improves over time, finds the best gear size, shape, and strength automatically. Why this is useful? So it reduces testing time and cost, ensures gears work reliably in real life, and it prevents failure due to material changes. So basically, in the Python code, I made a confusion matrix. So basically, what is a confusion matrix? So confusion matrix is a table that shows how well a machine learning model predicts things correctly or makes it mistakes. So how it works, it compares that actual results versus predicted results, and it has 4 parts. So basically, I've tried to link both the subjects that I've studied, the design of machine elements, where I've studied about gears, and robust design, where I've studied about confusion matrix, Taguchi, and all. Now I'll show you the Python code which I have written. So this is the Python code which I have written. Now I'll run the code. So the input which is asking is number of teeth. So I've given 20. Now it's jumps modulus. Poisson ratio I'm giving it 0.3. Bending stress I'm giving. Now context stress I'm giving 300. So basically this is the confusion matrix which I have arrived from the Python code. So it is the graph plotted between true label and the predicted label, and it shows the various values of various readings about how the gear design could cause robustness. So this is all about my project, and this is my entire Python code which I have written. So I went from the traditional robust design, so I used the Python code to implement machine learning process in robust design course. My name is Prakhar, course code 2178. Thank you, sir.